All right, here we are back at the inclined plane. You thought we'd never leave it. This is a lot different than we've had before. We're not going to have any kinetic friction. We're going to deal with static friction, which keeps the object rolling rather than slipping. So we have a uniform disk. We have a mass M. We have a radius R. And it's going down a ramp at angle theta. And so we're going to find an expression for acceleration. So just revisit our inclined plane, which is a little different this time. Here's our usual angle theta, but now I don't have a block. I have to actually draw a circle, which is not easy for me. Okay, so this is not really a free body diagram, but it's going to help. Okay, so we have the weight of the object acting down, but we are still treating it like all of the mass is at the center, so I'm going to draw that from the center of mass there. Now, the two things that I'm more concerned about here, not really concerned about here, is I have the normal force, right, acting from the surface perpendicular, and then we have the static friction force, and the static friction force is going to act in the backwards direction. And so this is the first time that not all of the forces are exerted at the center of mass. Believe it or not, it actually sort of makes things easier. Gravity is exerted at the center of mass and it acts straight down. The normal force is exerted at the contact point, which I just haven't drawn a very good circle, but you get the idea. The normal force there. And is it better? It's probably better in the book as well. The static friction is what keeps it from slipping, or also what causes it to roll. So what's actually exerting forces and torques that are going to make a difference here? Gravity exerts no torque. Okay, now this might confuse you because you might think, wait a second, gravity's rolling it down the hill, and you're right. But gravity is not causing it to torque, all right? Here's why. Gravity is acting at the center of mass. So if torque is equal to RF sine theta, if R equals 0, then gravity can't exert any torque on that disk, okay? Gravity acts at the center of mass. The center of mass is 0 away from the axis, so gravity doesn't exert any torque. The normal force exerts no torque because it's perpendicular to the lever arm. Okay, now I didn't draw the radius in, but you can, because I think that would make it messy, but the radius vector starts at the center and goes towards the surface. So the normal force is parallel or anti-parallel, if you will. Whether you think of it as 0 or 180, it doesn't matter. The sine of that angle is 0. So the torque doesn't exert, there's no torque exerted by the normal force. So what's causing the rotation? It's the friction, okay? Friction is acting perpendicular to the lever arm. As you can see, that angle is 90. And so that's what is causing the torque. So let's write our expression for torque is equal to the radius times the force times the sine of the angle between those two. So that is equal to the radius of the, what is this? A disk, excuse me. The static friction force, and the sine is equal to 1 there. We also know that torque is equal to I alpha. That's our Newton's second law formula. So we've got our RF is equal to I alpha. I for the disk is 1/2 mr squared. And we have our alpha in here. So now we have an expression for the static friction force. It's 1/2 mr alpha. One of the radius cancel out. So that's our expression for the static friction force. Now let's go back to what we know about the inclined plane. Okay, well, let's do our x equations. The sum of the forces in the x direction is equal to, well, now we still have gravity still pulling it down the ramp. So if you recall this from your inclined plane, what's pulling it down the ramp is mg sine theta. What's pulling it up the ramp is, as we've already drawn it, the static friction force. And so the sum of forces in the x direction are going to give us ma. And I could put an x there, but it is only accelerating in the x direction. So sometimes I get lazy and don't put that there. What about the y direction? Okay, remember the sum of forces in the y direction was 0. That's what made our life so much easier, right? Well, what's pushing up? The normal force minus mg cosine theta. And that is all, hopefully, review from unit 2, I suppose. So we're going to take our expression for the static friction force and we're going to plug it into this equation right here. Let's see what we get. mg sine theta minus 1/2 mr alpha equals ma. Now, you might be surprised, you might not. I go back and forth. The masses are going to cancel out. So g sine theta minus 1/2 r alpha equals acceleration. Now I'm going to substitute alpha equals a over r. And I'm going to get a equals g sine theta minus 1/2. And then if alpha is 1/2 r. And then if alpha is a over r, those are going to cancel out. So I get g sine theta minus half a equals a. Sorry, I'm trying to do this on one page. G sine theta equals 3/2 a. And so a is equal to 2/3 g sine theta. So that's our acceleration, our linear acceleration down the ramp. So we used our Newton's second law for rotating objects here. I guess we really didn't use this formula at all. I'm just so used to writing down my x and y formulas there. I suppose you could maybe use that to somehow figure out the coefficient of static friction there if you were given some information, but we didn't need that today. So instead of using our x and y equations like we did back in unit 2, we used our Newton's second law for rotating and for translating objects, and so we got a value for acceleration. And so we'll compare this to the acceleration if we were sliding down the ramp, right? Which, if you remember, is just g sine theta. So the acceleration is actually a little bit less when the object is rolling. That should make sense from a kinetic energy standpoint, right? If you can convert all of your gravitational potential energy into translating, then you're going to be going faster than if you've got to convert that into translating and rotating. So it should, I think what I want you to take away from this is, as well as what we did, was that this is less than if we were sliding, right? We'll talk more about that. So that should do it for this chapter, and your brain is probably full, so we've got lots of time to review.